Now, let us solve this given non-homogeneous higher order equation, but specifically the process involving the Wronskian of functions or variation of parameters. Take a look at this. I have placed here some of the necessary formulas, and I have also prepared another page because similar to the previous examples, we might need 2 pages and a lot of time in solving this. But the point here is this. We are going to consider the Wronskian of the functions given or functions identified later on, but basically the solution of this given equation is still expressed in the form of y sub c plus y sub b. As mentioned, y sub c is when this g of x is equal to 0, or in short, the general solution for an equivalent homogeneous equation of the left-hand side. But for y sub b, since in our table of particular solution we previously discussed, there's no row or trial particular solution for the square of cosine x. Hence, we are going to really use here the Wronskian of functions, but our y sub b is indicated to be having this kind of formula. Now, take a look at this. Once we were able to identify our y sub c, then we can identify our y sub 1 and y sub 2, which will also be part of our y sub b. The thing here is we don't know what are the u sub 1 and u sub 2, hence we have these formulas to cover for that. So let's do this step by step, and please bear with me. Let's start with the y sub c, as we will have here this given function or equation in terms of differential operator d. You'll have d squared plus 1 times y is equal to 0. Hence, our auxiliary equation is equal to, or is, m squared plus 1 equal to 0. To identify the correct general solution for y sub c, let's solve for the roots of this auxiliary equation. M squared is equal to negative 1. Taking the root of both sides, m is plus minus square root of negative 1. Hence, the roots are both imaginary. Now, following the format for imaginary roots, our a here is 0 and our b is just 1. We need this because the general solution for auxiliary equation for our y sub c with imaginary roots follows this idea: e to the power of ax times c sub 1 cosine of bx plus c sub 2 sine of bx. Plugging in the values, you have e to the power of 0x times c sub 1 cosine of x, or 1x, plus c sub 2 sine of 1x, or simply x. This is just 1. So our y sub c, which is the first part of our general solution, is c sub 1 cosine of x plus c sub 2 sine of x. This is just the first part of the process. And with this, following this form, we know that this would be our y sub 1, and this sine x is our y sub 2. We need this because that's the same, or these are the same functions to be plugged in for y sub p. And at the same time, since our u later on will use Wronskian, these are the functions involved in the identification of Wronskian of functions. You have cosine of x and sine of x. Now, if you would like to review a specific video on our playlist, on this playlist, we were already able to solve for the Wronskian of cosine x and sine x. The value of that is just equal to 1. If you're not yet convinced with this, I beg you to look into that video. There is a discussion in solving for the Wronskian, but I might also present here the necessary matrix that came up with 1 here, because we also need this for w sub 1 and w sub 2. The Wronskian of functions is simply the determinant of this given matrix, where the first row are the functions themselves, and the second row are the first derivatives of each. The derivative of cosine x is negative sine x, and derivative of sine x is positive cosine x. This was used to solve for 1. Again, the link is provided below for the previous video. Please try to view that on your own time. I am representing this because these are very important in solving for w sub 1 and w sub 2. W sub 1 is actually a Wronskian as well of specific process where the first row, because it's W sub 1, the first entry will become 0. In the last entry, if there are many entries here, but since this is a 2 by 2 matrix, hence that will be on the second row, is this given function here, the square of cosine x. But the second row will just be the same row as the column rather, would be something like that. Okay, so that's for our Wronskian 1, or the first Wronskian. For our W sub 1, for our W sub 2, same process, but it will be the second row, which will be substituted by this same expression, and the first column would be the same column here. Okay, so simply get the solve for the Wronskian of each, which of course follows this idea, multiplying that, but that's just equal to 0, and then multiplying this. So you'll have here minus, take note, that's the different diagonal, cosine squared of x times sine of x. In short, our final W sub 1 is negative cosine squared x and sine x. For our second here, we will be multiplying this. So we have here cosine x times the square of cosine x minus this other side or diagonal is 0. Hence, we'll have this form, the cube of cosine x. With this now being our W sub 1, and this is our W sub 2, going back to the formula, we can now get the intended U prime sub 1 and U prime sub 2, which will be used later on to come up with the correct U's to be paired with Y sub 1 and Y sub 2. So it would be the ratio of both. Let me use the spaces here. So U sub prime of 1 is actually the ratio of W sub 1 and the Wronskian. And for U prime sub 2 is W sub 2 over the Wronskian W. Take note that our Wronskian is just 1, so whatever will be the value of W sub 1, W sub 2, it would be the result. So you have negative cosine, this one here, squared of x sine of x over 1, so it's just again negative cosine squared x sine x. Then this here is just cosine cube of x over 1, or simply cosine cube of x. So we now have our primes and prime here. Take note, they will be used later to solve for this. Now let me use this second page because I believe the spaces here are not enough because we are going to integrate them to solve for U sub 1 and U sub 2. In short, let me copy these values, copy, and go to my next page where I already posted here the different formulas as well. So this is the formula that we're going to follow now. So let's solve for our U sub 1, which is just the integral of U prime sub 1. And this time, please don't forget that d of x will appear here because we are now integrating with respect to our variable x. So it would be like this here. So it would be the integral of your U sub 1, U prime sub 1 rather. You have negative cosine squared x sine x, and then you'll have here dx. Right? For your U sub 2 is the integral of U prime sub 2. Let us have it later, okay? Because we're going to attack this one step by step. Now, to integrate this, of course, you need to decide what would be your U du, because you can have here either cosine squared of U du or sine of U du. However, we always consider the exponentiation and then place the negative sign together with sine x. You will have here cosine squared x, and you will have minus sine x dx. That's because the derivative of cosine x is just, or cosine itself, okay, cosine x is just equal to sine x, okay, negative sine x. This is also true with what will happen next. In short, this can be expressed in this manner, okay, squared of cosine x. It could be expressed like that. minus sine x dx. Now it falls to this one here, and using the law of exponentiation or the integration for an exponent, you will have here cosine of cube over 3 plus c. Of course, we need to have plus c, but in the meantime, let's stay with that. In short, you will have here your form, which is equal to 1/3 cosine cube of x. This is your u sub 1. Okay? Now for your u prime sub 2 again, u sub 2 is the integral of u prime sub 2, which is u prime sub 2 is this one here. Okay? So you have the integral of cosine or the cube dx. Okay? Take a look into this. Similar to what happened earlier, when we have the integral of cosine, we need du, which is the form of minus sine x dx. But we don't have sine x here. There is a strategy that we could apply here, breaking this cosine cube into cosine squared of x and then cosine x dx. Still, this is not a derivative of cosine, but what we could do here is this. Let me transfer the exponent on the other side, because we can, by identity, cosine squared of x could be written as 1 minus sine squared of x, and we have now negative sign here. So this is what will happen here. Cosine of x times 1 minus sine of squared x dx. Still, we have 1, so we can distribute that. You will have here cosine x minus, and you will have here times the integral of cosine x times sine squared of x dx. Okay? But here, this will not be du of this. It's the other way around, because this has exponent. What will happen here finally is the cosine, this also should have dx here, pardon with that, because it to be integrated, you have something like that, cosine x dx. Okay? You don't need to worry about this too much, because we have already the equivalent of that if we don't have exponent. And then we have here sine of squared x cosine dx. This is its u du. Okay? U du. It's the other way around. So what we have here finally, I don't have much space. This would be the integral of cosine x is just simply sine x. Sine x. And you will have here minus, you will have the cube rather of sine x over 3. This is our u sub 2. Okay? So this is our u sub 2. This is our u sub 1. This should be integrated with our y sub 1 and y sub 2. So let me also add another page here. Okay? So because our y sub p should be u sub 1, y sub 1 plus u sub 2, y sub 2. And our y is equal to y sub c plus y sub p. So our y sub p now is equal to u sub 1, y sub 1 plus u sub 2, y sub 2. Going back to the previous page, our u sub 1 is this 1/3 cosine of cube x. So you have here 1/3 cosine cube x. And our y sub 1 in the previous page, pardon for this, this is our y sub 1 cosine, and the y sub 2 is sine. Please help me remember that. You will have here times cosine x plus your u sub 2 in the previous page is this here, sine x minus sine cube x over 3, sine x minus sine cube x over 3 times your y sub 2, which is also sine x. So simplifying that, you have 1/3 cosine 4th power of x. Distribute that. Cosine, that's sine. Sine squared of x, and you have here 1/3. You could also try 1/3 here if you would like to. 1/3 sine cube of x. Okay? So now, we have this as our y sub p. Finally, y is y sub c plus y sub p. Let me copy the y sub c earlier. Okay, copy. Let me place here the y sub c, removing this and that. So finally, we have this our solution. C sub 1, and you will have here cosine of x plus C sub 2 sine of x. That's for our y sub c. Plus your y sub p 1/3 cosine fourth of x plus sine squared of x minus 1/3 sine fourth of x. We cannot combine these two into one identity because this is negative. And with that, with all of these processes, we ended up with our answer, the final solution of the given equation. As you can see, very long, but we all need this to understand the process we're doing. This is the answer to this item. Thank you very much for watching.